Hey everyone, this is Manas, your friend and tutor. And guys, we are kicking off with a brand new series on theory of machines. Well guys, I've designed this module into two parts. In the part 1, we'll talk about kinematics of machines, and in part 2, we'll see dynamics of machines. Well, it has a whole lot of subtopics, but in today's lecture, we'll kick off this session with the velocity analysis of a 4-bar mechanism. And this is a very popular term if you are a mechanical engineer. And in this video series, you'll see a lot of mechanisms and their corresponding velocity analysis. So let's kick off with problem number 1, and here we go. So here we are, there is a 4-bar mechanism in front of us and its dimensions, all of them have been given to us. And if I can just name a few, you can clearly see that this angle over here, this over here is the angle DAB, which has been given as 60 degrees. So you've got to take that into account. Now, first of all guys, if you're watching this video, I would suggest all of you to get a piece of paper, preferably an A4 size piece of paper. This would do the job. This is where I made the diagram. And secondly, get a pencil, okay, and also get a roller scale or even a mini drafter. That will do the job. Now, you need a rounder also, or a compass, whatever. Now, what we need to do is we need to recreate this stuff into your plain sheet of paper, and I'll show you how this can be recreated very quickly. And then corresponding to that, we also need to make its velocity diagram, right? So here we go. What we'll do initially, I'm going to draw this, and this is nothing but AD. AD has been given to us. Let me see, that is going to be 100 millimeters. Now for this configuration diagram also you can take a scale, okay? And now the scale that I have taken is nothing but the full scale, 1:1. Don't worry, take all these dimensions, and these dimensions are such that they will fit in properly, and they'll also take very less space in an A4 size piece of paper. Don't worry about that. These dimensions are very small and very comfortably they'll fit in. And then we have this point A and this point D, and then just make this sign. This is the grounded sign, okay, just to ensure that this link has been fixed. Secondly, what we want is point B, and point B's distance from A is 50 millimeters. So here we go, and this angle has to be taken with the help of a protractor, and that's 60 degrees, and here it is. Simple. From B to C, how much is the distance? Well, that's 66 millimeters. So guys, in your compass, you need to take a radii of 66 millimeters, and then with this fellow B as the center, you just need to put an arc over here. Similarly, again, somewhere along this arc, we have point C, and its distance from point D is how much? Well, it's 56 millimeters. So again, with 56 millimeters as the radius and with this D as the center, you need to cut an arc yet again, and this is going to give you point C. And now let's join C with B and C with D. So this is pretty much done. Now we sort of have a projected portion in this link BC, and also in link CD, and we are going to make that also, okay? And once we recreate the configuration diagram, then it's going to get very easier for us to make the corresponding velocity diagram. So point F, let's read about point F. Although it has been given in this 4th part, there is an offset point F in the link BC. FB has been given to us 45 and FC has been given to us 30 millimeters. Okay, so from B you need to cut an arc of radii 45. So with B as center, you need to cut an arc having radii 45 millimeters. Do the same stuff. Now with a radii of 30 millimeters, and then with this fellow C as the center, cut an arc again, and this point guys is your point F. And you can clearly see BCF is read clockwise. So B, C and then F. That's why we took these arcs below BC. Had we taken them above BC, then it would have read anti-clockwise, which is not a condition given in the problem. Okay, I hope you can understand this. Read clockwise. Anyway, we've got one more point, that is this point G. Again, G has to be put up in such a manner that B, where is it? DCG is read clockwise. DCG is read clockwise. So again, we are going to put arcs here only. Fine. So we've got CG. CG is equal to how much? 24. So with C as center and 24 as radius, cut an arc. Just put an arc rather. And then with DG as 44. So in your compass, take 44 as the radii. With D as the center, cut an arc. And this is going to give you point G. So join G with C and D. That's it, guys. This is exactly how you need to recreate the configuration diagram from the problem on your book onto the piece of paper in which you are making the drawing. And in that same piece of paper, now we are going to create the corresponding velocity diagram. Okay, and here we go. Okay, there is a point E also, right? Where the hell is this point E? Well, point E is at a distance of 40. So just what you can do is, from this point B, keep your scale, okay, 40 millimeters away, place a point, and that point is point E. Well, what we have to do is we need to find this point E's velocity, okay, with respect to this grounded or fixed point, you can say fixed link. Anyway, that is something we'll take up later on once the velocity diagram is over. Right now, let's go ahead. So what we do have is this link AB. This is also a crank, you can say. This is having an angular velocity of 10.5 radian per second in the counterclockwise direction. So something like this. Okay, let me just write this. Omega for what? AB, you can say. Omega for AB has been given as 10.5 radians per second, right? Now we know that velocity of this link AB or BA, whatever, is equal to what? Omega multiplied by the radius of what? AB, or the length of the link itself. V is equal to omega r. Linear velocity is equal to angular velocity multiplied by the radii. So fine, this can be calculated very easily, and if we just put the value 10.5 radians per second, 10.5 radians per second multiplied by this velocity, multiplied by this radius. Well, radius is how much for AB? It's 50 millimeters. Just try to convert this into meters. 50 by 1000, isn't it? That means 0.05. And this is in radians per second. This is in meter. So the final value that you all will get will be somewhere around, let me see. Well, that's 0.525. Okay, 0.525. That's 0.525 in meters per second. Now, let us talk about making the velocity diagram. How can that essentially be done? So here we have it. We need to take a scale. Okay, so the space that I have, on that basis I have taken this scale. 0.525 meter per second, let's say, is equivalent to 50 millimeters, right? In that sense, if you take this over to the right hand side, 50 divided by 0.525, what will remain here is 1 meter per second, and once you do the division, it is going to be equal to 95.24 mm, and if you take this 50 over to this side, you will have 1 mm. 1 mm is equal to 0.0105 meters per second. Well, you guys might be wondering why I am doing this conversion, because, well, it's going to be useful for us. After we make the velocity diagram, it is going to help us convert the distances into meters per second or velocities. Let's kick off. First of all, we need to mark the point, or we need to just mark a point which is fixed. Okay, here we go. So this is the fixed point, A and D. Done. We are going to kick off with this AB link, and you can clearly see this AB link has a sort of counterclockwise direction. So it is going to, if it completes one revolution, this B point will tend to make a circle. Okay, and somewhere here at an angle of this is how much? That is 60 degrees. It is going to have a direction somewhere here. This is going to be the direction of velocity B, isn't it? So what we need to do is, you need to keep your roller scale absolutely perpendicular to this link AB, something like this. Keep your roller scale absolutely perpendicular to this link AB. Okay, you have markings over here, and let's say one of those markings, overlap it with this line AB, and this line will automatically become perpendicular. That's the easiest way to ensure perpendicularity. Okay, roll it until you reach here. Draw a line. That's it. This line is how much long? That is 50 millimeters long. Okay, remember this. Fine. Let's write over here B. This is nothing but the velocity of point B. Now what? We want to locate point C. Now again the same stuff. Keep your roller scale perpendicular to this BC. Okay, something like this. Roll it until you reach here. So we are locating C with respect to B. Okay, roll it until you reach here. and then randomly just draw a line. Make sure that the line that you've drawn is very light. Fine. Is there any other way we can locate C? Well, we can locate C also with the help of this fixed point D. Well, keep your ruler scale perpendicular to this link CD, somewhere like this. Okay, this angle is 90 degrees, you know that. And then you roll it until you reach this D, and then draw a line which in fact intersects. Okay, intersects somewhere here. And guys, this point is what you refer to as point C. So that's point C. Now let me get rid of this construction line, and this is the vector. Okay, so VB with respect to A, you can say. This is VC with respect to B, and this is VC with respect to what? D or A, whatever you can say. And finally, you can even write this relationship, this and this, same order, this in the opposite order, triangle law. I'm sure you must remember this from your 11th grade physics. And this is VCA is equal to what? VBA plus VCB. Okay. So two vectors in the form of velocity in magnitude and direction in the same order, the resultant in magnitude and direction in the opposite order. That's it. So what's next? So we've got all these points A, B, C and D. Now we need to work out where F is, we need to work out where G is. Now what we're trying to do is we want to find point F. With respect to link BEF or FB, keep your roller scale absolutely perpendicular with respect to link FB and bring it over to this point, small b. Just draw a line randomly, okay, very light. Then with respect to link CF, keep your roller scale absolutely perpendicular to this link CF and bring it over here to point C and then draw a line. The intersection, guys, is going to give you point F, and that's point F. Okay, now let me do the embellishments, and there you have it. That's point F. Okay, what else? So we've got to locate point G. That can be done very easily. Keep your roller scale absolutely perpendicular to this CG. Okay, then roll it until you reach here, that is C. We are locating G with respect to C. Again, I am reiterating, keep your roller scale absolutely perpendicular to this link CG, okay, and we are locating G with respect to C. So roll it down until you reach C and then draw a line. Simply draw a line. In the same manner, keep it perpendicular to, keep your roller scale perpendicular to DG, roll it until you reach D and then draw a line. This intersection point of both the lines is going to give you point G. So we are pretty much done with the velocity diagram, and the only stuff left is this point E. Okay, we will take a look at that later on. Right now, let's focus on what different stuffs we need to calculate. Okay guys, so the first thing is velocity of point C. Velocity of point C. So point C is right here. Okay, velocity of point C. Fine. So you need to keep your scale over here. Okay, and just try to measure this from C to A. Let me write this, C to A, and this measurement is going to work out as 38 millimeters. Okay, if you have taken the same scale, just if you have taken this scale, 0.525 meter per second is equal to 50 mm, you will get this value. Okay, and this is in millimeters. Now we know how much 1 millimeter is in meters per second. So what we'll do is we'll try to make use of this, multiplied by 0.0105. Now this will automatically get converted in meters per second, and the final value that we are going to get, let me check, this is very close to 0.4 meters per second. Okay, so the velocity of point C is how much? Well, that's 0.4 meters per second with respect to this fixed portion, or with respect to A, you can say. Secondly, we need to work out the velocity of point E, this point. This point is somewhere along BC. Now this point is at a distance of how much? This distance has been given. Well, that's 40 millimeters. Okay, and this point will have a corresponding point over here also in the velocity diagram. Well, how can that be worked out? We need to see. So here we go. What do we need to find? We'll have it somewhere here. Let me show you rather. We'll have it somewhere here. Okay, let me put a point over here. We'll have it over here. but how can we locate that point? So watch carefully. Here we'll have point E. Why I'm telling you this? BE, this is BE over BC is equal to, again, BE in the configuration diagram over BC. Now guys, what basically I've done, these two figures are proportional, or these two diagrams are rather proportional. Hence the ratio of different sides are also going to remain same, and this is the policy which I have used here. Okay, so how much is BC? Well, that has to be worked out. So what is BE rather? So BE will be equal to BE over BC. How much is BE? Well, that's 40. Let me just put it over here. Divided by BC. BC is how much? I need to take a look. Well, that's 66. Multiplied by this value. How much is BC? Well guys, you can actually measure this, and BC will work out as 32 millimeters. Okay, just do this measurement from B to C with the help of a scale. Measure this works out as 32 millimeters, and once you do this calculation, the final answer that you will get is 19.39 millimeters. 19.39 millimeters. So this is how much? This is 19.39 millimeters, or rather 19 millimeters. You cannot put a you cannot really put a point how much away? 19.39 millimeters away. Okay. Anyway, either 19 or 20. Just take it as 19 or slightly more than 19, and then place a point over here from point B, and then you connect that point with this. Okay. So here we have it. VE, measure this from E to A is equal to EA, and this is going to work out as, let me see, 39 millimeters, isn't it? And then you need to do the conversion. It's pretty easy. 1 mm is equal to 0.0105, and this will work out in meters per second. And guys, just do the calculation. It's pretty easy, and this is going to work out as, in two decimal places I have written, 0.41 meters per second. So that's it. That's exactly how the velocity of point E somewhere between B and C can be worked out with respect to this fixed point. Very easy. Then we need to find the angular velocity. Now guys, remember, there is a relationship V is equal to omega r. Similarly, omega can also be written as V over r, and we are going to use this omega for what? BC. Okay, omega BC is equal to V BC divided by r. R is BC itself, this length BC. So how much is VBC? So from B to C, you need to calculate this distance BC. We know how much BC is. We already calculated it. It's how much? Well, that's 32. Okay, so that's 32, but it is in millimeters, and in order to convert that into meters per second, what you need to do is you need to multiply that by 0.0105. Now it's converted into meters per second, and this BC is how much? This is 66 millimeters. In millimeters, convert that into meters, 0.066, and just do the math. This is going to work out as 5.09, and since this is angular velocity, you need to write radians per second, and that's it. In the same manner, we'll go ahead and find omega CD, and that will be V CD over CD itself, V upon R. Okay, so how much is CD? C to D, you need to measure this distance, and as far as my calculation goes, CDE will work out as somewhere around 38 millimeters. Okay, 38 millimeters. You just multiply that by the scale. Okay, 0.0105, you'll get this 0.105, will get this converted into meters per second, divided by CD. What's CD? That's 56 millimeters, and you just put this value 0.056 in meters. Okay, and just do the math. This is going to work out as 7.125 radians per second. 7.125 radians per second. So that's it, guys. Finally, we need to find the velocity of an offset point f. Okay, you need to find the velocity of f with respect to this fixed length. So measure this f to a with the help of a scale. Do this measurement. Let me just write this. Vf is equal to fa, and this measurement will work out as 48 millimeters. And you know the drill now. In order to convert this into meters per second, here we have it, 48 multiplied by 0.0105, and on doing the math, the value that you will get is 0.504. 0.504 meters per second. That's it. In the same manner, we can go ahead and calculate this G. Vg. Okay, and this is going to work out as G. So from G until we reach here, that is A, you can make the vector like this. Okay, so this is the triangle, and looks pretty good. Vg with respect to A, this is Vc with respect to G, and this is Vc with respect to A. And you can also write an equation like this. Anyway, we want Vg, so from G to A, measure this length Ga from the velocity diagram. This measurement will work out as 30 millimeters, and again the same drill, 30 multiplied by 0.0105, and this will give you the corresponding value in meters per second, and it works out as 0.315 meters per second. So guys, this is pretty much what needs to be done, and this is exactly how all the values at different points on the mechanisms can be worked out in terms of velocities. So guys, that's all for today. I'll be back with a new problem. Until then, take care and have a nice day. Thanks for watching.